Welcome back to GC Lalshier's Physics. Like the last topic on quantities and units, uncertainties are not very interesting. In fact, they can be quite tedious, especially in labs, but they're also very important in the real world of physics and engineering, and a working understanding of them is an important requirement of AP Physics courses. So let's take a look at them. Up until now, you've probably studied a lot of math, and you might have done some calculations with physics formula, but have you actually tested them in the real world? A measured value can't be known precisely, so neither can anything we calculate using that value. The degree to which a measured or subsequently calculated value is known, or rather, to what extent it's unknown, is called its uncertainty. Uncertainty is often called an error, but this is technically not correct. It's just that every measuring device has its limitations, even if it's used perfectly. So uncertainty is not a result of any error we make, but it's like an error in that it reflects a difference between our measured value and the real value. Let's take a look at a math problem as an example. Calculate the area of this circle. Now, we know the area is pi r squared. I'll use 3.1415 for pi, but you'd probably be best to use your calculator function because it's more accurate. If that circle is actually one side of a cylinder with a known height, we could use that to calculate its volume, and then if we knew its density, we could calculate its mass. As a math problem, everything here would be fine, and we might just round our answers in order to not waste time writing out lots of digits. But in physics, how we round our answers is important because it suggests something about how close we think these calculated values are to the real ones. At the end of this video, we'll solve this problem as we should in physics and round it correctly. Now let's say that we measured the radius of the cylinder with a tape measure whose scale is only in meters. Now that makes it a fairly useless tape measure, but it'll work for what I'm trying to show in this example. Assuming it's nevertheless a reliable tape measure, then we can probably determine that the radius is somewhere between 10 and 10.5 meters. But anything more precise than that would be little more than a good guess. That brings us to the basic uncertainty rule for measuring devices. The uncertainty in a measuring instrument is usually half of its smallest scale. Now, we could probably write 10 meters is less than the radius is less than 10.5 meters. But since we often don't know whether a value is larger or smaller than the measured one, we usually express an uncertainty with a plus or minus symbol. So we could either write 10.5 plus or minus 0.5 meters, or 10 plus or minus 0.5 meters. For simplicity's sake, I'm going to assume it's 10 plus or minus 0.5 meters. If we measure the height of the cylinder with the same tape measure, so it has the same uncertainty, then this blue cylinder represents the cylinder's most likely measurements. But its size could also be up to this larger cylinder. And although in this case it's unlikely, based on our measurements, if we were just given the measurements with the uncertainties, as we usually are in physics, then we could also have the smaller cylinder. If we then calculate the volumes of all these possible cylinders, we see that we have a range from the smallest here to the most likely here to the largest possible volume here. And then if we assume a known density of exactly 2,000 kilograms per cubic meter, we get this possible range for the mass of the cylinder. Given that our range can be anything between 5 and 7 million kilograms, it seems pointless to write out all these decimal places, some of which represent a tiny fraction of a gram. And in physics, it would actually be wrong to do so, as we'll get to soon. So let's round it off to what we call one significant digit, or one significant figure. While we're there, it would also be better to write a number like this in scientific notation, which is also called standard form. So here's how I'd suggest writing the final answer to the mass of the disk, which we calculated using measurements which we could have taken using that tape measure with its scale only in meters. Why does all this matter? Let's imagine that we're talking about this cylinder here, and say it's supported by this beam. The beam will be made to withstand a certain weight force, and that force will also have an uncertainty. Engineers need to know that even if the cylinder is heavier than planned, and the beam is weaker than planned, it will still be able to support the weight of the cylinder so that it doesn't fall down onto the shoppers below. However, the truth is that uncertainties are much more complicated than they're presented in high school physics courses. We can't say for sure that the mass of the cylinder is between 5 and 7 million kilograms. In reality, there's a probability distribution of possible masses of the cylinder. The most likely mass is the one we calculated from the measurements we took, in this case 6.3 million kilograms. And the probability of it being other weights becomes lower and lower as we get further and further from that 6.3 million kilograms. It's not necessarily a normal distribution as shown here. In determining the actual probability distribution would require knowledge of statistics well beyond high school level, and well beyond mine. The important thing in high school physics is not to present a measurement or a calculated value with a greater level of certainty that is, with a lower uncertainty or more significant digits, than can be realistically determined from the measurements involved. Now let's look at the main two sources of uncertainty in the laboratory. The most common type is called a random error, but again, it's not usually an error. It just comes about because measurements are not perfect. For example, the edge of the cylinder might be rough, so the radius might be different at different points, and it might not even be perfectly round. Our eyes aren't perfect either. The best solution to random errors is to take measurements lots of times and average those values, as then the random differences should at least partially cancel each other out. There's sometimes more than one way to repeat a measurement. For example, if measuring the time period of a pendulum, it would be possible to measure the time period of one cycle and then repeat the whole process 10 times. But it would usually be more accurate to measure how long it takes to swing for 10 cycles and then divide that time by 10, because that way the random errors at the start and end of the time measurement would each only occur once, instead of up to 10 times. This technique of taking repeated measurements often comes up in AP Physics exams, when students are asked how an experimental method could be more accurate. And if you're asked to plan an experiment, I suggest saying to take measurements lots of times and average them. The second type of uncertainty is called a systematic error. These are the same for every measurement, so taking a lot of measurements and then calculating the average won't work for a systematic error. A common systematic error is a zero error, which occurs when the scale of a measuring instrument, such as a micrometer, isn't perfectly aligned. The solution to a systematic error is to add or subtract it to your measurements to cancel it out. Once you've determined your uncertainties in the laboratory, you need to apply them in your calculations. The College Board recommends using these propagation of error rules. However, there are many different systems and rules for uncertainties, so please follow your teacher's guidance in your laboratory work. The most important thing at AP level is that students understand that every real-world measurement has an uncertainty and can apply or propagate these uncertainties in calculations, and suggest ways to reduce or minimize the experimental uncertainty in a given situation. Although it may be an acceptable answer to some questions, I get a bit frustrated when my students often suggest using better or more precise measuring equipment. It's usually true, of course, but any scientist at any level can improve the accuracy of their experiments by using better measuring equipment, so this answer doesn't show much insight. Instead, I suggest generally thinking about how to reduce the uncertainty with the equipment made available to you, or at least, if allowed, with things that a student might have available. For example, in measuring the time period of that pendulum from earlier, students could perhaps use a smartphone or other camera to record it, and then analyze the video in slow motion in order to measure its time period more accurately. And always remember, if in doubt, repeat, 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 and take averages. Before we go any further, let's take a look at which situations to use which approaches to uncertainties. I'll make them all about cylinders so that they're easier to compare. First, let's consider a totally theoretical problem, like a derivation. Deriving is an important skill in AP Physics, which I'll cover in a later video. For example, you might be asked to derive the mass of a cylinder based on its radius, height, and density. In that case, you could just algebraically rearrange these formulae to derive a new formula for mass. In this case, you don't need to worry about uncertainties at all, because no measurements were made. But what if you used a similar formula in the laboratory, where you might be asked to determine the density of a given cylinder as accurately as possible, using supplied measuring equipment? This could also happen in the real world of engineering. In that case, you'd probably want to use uncertainty and propagation of error rules, which are what we've covered up until now. But what about all those ordinary physics problems which aren't connected to the lab, like the ones you need to solve for homework and in your exams, or like the calculation of the mass of the cylinder from the start of this video, which we'll return to at the end? For these, we use an approximation to uncertainty called significant digits, which are also called significant figures. This is what the rest of this video will be about. Since we're not talking about the lab anymore, let's now look at a real-world problem that doesn't even need physics. Let's say your friend tells you that she left her lunch at home, but she's too busy that day to go and get it. So, as a good friend, you offer to go and get it for her on your bicycle. You don't know where she lives, and all the houses in the street look similar, but she tells you that she lives 4 kilometres up the road. Now, we'll need to assume that this is back when I was at school before smartphones, although we'll say that you have a trusty bike computer called an odometer, which records the distance you ride. So, you reset your odometer to 0 and off you go. Now, even though she said 4 kilometres, you'll probably want to start looking for a house after about 3.5 kilometres. And if you get to 4.5 kilometres, you'll probably figure out that you've gone too far and turn around. So by saying 4 kilometres, we can assume that she probably means somewhere between 3.5 and 4.5 kilometres. In physics terms, we could say, in this case, you're assuming that a distance given as 4 kilometres has an uncertainty of around 0.5 kilometres. But let's now say that she knows that she lives exactly 4.3 kilometres away. If she tells you this, then you could assume that she lives between 4.2 and 4.4 kilometres away, or perhaps even 4.25 and 4.35. Thus, we could probably know immediately which house is hers. So adding that 0.3 to the 4 not only increases the distance, but it also increases the assumed level of precision, or in physics terms, it decreases the uncertainty. But what if she knows that she lives exactly 4 kilometres away? Then she can say 4.0 kilometres. While in math and most everyday life situations, 4 and 4.0 mean the same thing, in physics, the 0.0 has an important meaning and must be kept, because it indicates a higher level of precision. We can say that 4.0 has 2 significant digits, while 4 has only 1. So let's take a look at some significant digit rules. Rule 1. All non-zero numerals are significant. This is quite straightforward. Rule 2. All zeros between non-zero numerals are significant. Likewise, pretty straightforward. Rule 3. All zeros after the first non-zero numeral and after the decimal point are significant. This just shows that zeros before the first non-zero numeral are not significant. 3a is just 1a divided by 10,000, and 3b is just 2a divided by 10,000. And when we multiply or divide something by a number which doesn't have an uncertainty or significant digits, then the number of significant digits should stay the same. For rule 4, it would be unlikely that we'd write a number with zeros before unless there's a decimal point as there is in 3a, but if we did, then those zeros wouldn't be significant. And we just covered rule 5 before with an example of 4.0 kilometres. Finally, it's often best to express a very large or very small number in scientific notation, which is also called standard form, and all the digits we use before the power of 10 are significant, so we can just add zeros to show a high number of significant digits. I should mention one possible exception to these rules. Let's say we subtracted, or added, 2 numbers with 4 significant digits, and got an answer of exactly 400. Then, as we've already shown, we could just write it as 400.0. But what if we had added or subtracted numbers with 1, 2, or 3 significant digits? All those answers would be 400, but that could include 1, 2, or 3 significant digits. Physicists have a few ways to solve this problem, but I just recommend my students to write the number of significant digits as SD or SF for significant figures after their answer. Finally, let's go back to that original problem and answer the questions using significant digit rules. Please note that I'm assuming that the radius measurement contains 3 significant digits and the height measurement contains 2. Although the actual calculations are similar, now I'm assuming that we were given this problem for homework or in an exam, and our job is just to use those given significant figures to round our answers correctly. The golden rule of significant digits is that a final answer should be expressed with the lowest number of significant digits given in the question. Just as a chain is only as strong as its weakest link, a calculation is only as accurate as the least accurate number used. Since pi is known very precisely, we can use lots of decimal places or just use the function on our calculator, so we'll get lots of significant digits in our final answer for the area. But since we used the radius, which is given to 3 significant digits, we should round our final answer to 3 significant digits too. However, to calculate the volume, we should use all the significant digits we have, because this is still the most likely value of the area, so we should use it in all subsequent calculations. Please be sure to show, in your working for each part of a question, which is your working with many significant digits, and which is your final answer, rounded to the correct number of significant digits. Then, for the mass of the cylinder, we should use the unrounded answer to volume, but we should round our final answer to 2 significant digits, because its mass, unlike its area, depends on its height, which is only given in the original question to 2 significant digits. So, to conclude, the golden rule of significant digits is always round your final answer to the smallest number of significant digits given in the original question. But actually, the real golden rule is think. Sometimes, none of these rules apply, and you'll need to find your own way to decide how to round your final answer. Just try to write your answer as precisely as possible without suggesting a higher level of precision, that's without writing more significant digits, than we can realistically know. As always, thanks for watching.